told more people.
Okay.
At least one of them said he will show up today.
Okay.
Hopefully, I'll be fine.
Yeah. Yeah, it's something that's a little bit hard to
I think the
jump
first thing-
in the middle.
Well, he knows OCaml. He knows OCaml.
Right.
His PhD thesis is on generative metaprogramming using OCaml.
I see.
So I assume he's familiar with some basic things.
Right.
If you know OCaml, you've probably seen some awesome ones.
Right.
So I think he'll be able to just jump in.
All right, I'm going to adjust the lights and let's get started.
Extending it, it's like he doesn't know how to do it. See here so you can see.
All right, we're going to get started then. Good morning, everyone.
Good morning, Dave.
Today is the fun day or the scary day, depending on how you look at it, because we're concentrated on these three sort of related topics in Haskell: functors, applicative style, and monads. And then I've taken the liberty of rearranging the schedule slightly. The do notation and I/O that we were going to talk about on Thursday, I think it probably makes more sense today, and I think we'll be able to get through it. So as you're following along here, are we all ready to start? You guys are ready? Yeah. As you follow along here, I thought what we would do is we would return to our example from yesterday that we were developing, but we'll kind of develop it again from scratch as a little bit of review, and then use it with these topics that we're talking about today. So starting with the review, then. So yesterday we developed a kind of system for keeping track of live coders, their names and their preferred languages, and calculating an imaginary cool factor on the basis of their language choices. So let's kind of develop that again, but much more quickly than we did yesterday. And let's maybe do it in a different order too. So let's assume that our overall task is to keep track of live coders. So we might make a type for the live coder. Live coders have different characteristics that we want to keep track of. So using Haskell's record syntax makes sense. So this live coder here is the name of the type. This live coder here is the name of the constructor for that type. This could actually be a different word if we wanted to. If we wanted to call this an actual live coder, that would actually kind of make sense. But it's not very idiomatic. It's very common in Haskell to have these types where the name of the type and the name of the constructor that makes the type are the same. And then the curly brackets here means we're using Haskell's record syntax, indenting two spaces. And in the record syntax, we have the names of fields with their type separated by commas. So a live coder might have a name, which could be a string, and we also gave them a language yesterday. And so kind of doing this top down instead of bottom up, let's just imagine that there's a type for a live coding language. That type doesn't exist yet, but we can be quite confident that we can create such a type and give it meaningful logic, meaningful semantics. It's very useful, as we saw, to have types that we make automatically derive type classes so that we can do things like print the type, compare the type to other instances of itself, that kind of thing. So there's this common set of type classes, show, which lets it be turned into a string for printing. That's super useful. EQ for letting it be compared to other instances of the same type. And ORD, maybe, for, I don't think we need ORD in this case. I think show and EQ is enough. Actually, maybe we don't even really need EQ. We could be minimalist and leave it off until we need it. But we pretty much know we're going to need show. Why do we know we're going to need show? Because we're going to test all these things in GHCI's interactive prompt. We test them by evaluating them, and then it has to print them. So to print them, it has to turn them into a string. That's not going to work if we can't convert this type into a string. So auto-deriving show makes sense. We're going to have a type for our live coding language. So let's do this again, live coding language. And we did this as yesterday as an algebraic type. In other words, a type where we have some large number, or more or less large number of constructors, each of which represents some unique position in the space of that type. So we had lists like super collider, extempore, tidal cycles, hydra. All of these should be separated by the bar. And again, it's useful to derive things to auto-derive instances for our new type. So we can test that already. I'm going to save it in my home directory as, I'll call it day2.hs. And I'm going to fire up GHCI and going to load day 2. And didn't show you this yesterday, but let's say that we just loaded this and we wanted to know what was in this thing that we just loaded. There's another one of these helpful things you would find about in GHCI's interactive help. That thing is browse, which gives you a list of things that are in your current context. So here we see pretty much the same stuff that was in the module that we just saved. But maybe if our module that we just saved hid a few things, maybe we wouldn't see everything that was in the module. We would only see the things that that module exported. Anyway, browse is really useful. It kind of shows you what you have at your disposal here. So here in the results of browse, I can see that because of my programming 3 minutes ago, I have some stuff connected to these two types, live coder and live coding language available. And I could make a live coder value by having the live coder constructor, some name, a string, and a language like supercollider. And because both of those types derive show, it's able to take that type that I just made and turn it into a string for us and give it back to us. Super exciting, I know. Got back exactly what, more or less exactly what we put into it. All right. So there's one little tangent that we didn't talk about with the record syntax that I just wanted to kind of mention before going in more substantial directions today, and that's that there's another way of constructing values in the record syntax. So here in the terminal, you see me constructing a value by putting the constructor live coder and then I'm just putting values for the fields in the same order that they appear in here. So that makes sense for various reasons. Most of all, that it connects with this idiom, which we didn't show. And it's kind of an older Haskell idiom. We also can make types using the data declaration where the type has some name, and then it has some constructor, and then what comes after the constructor are the names of other types. So the way that we've done the live coder there, it's not entirely unlikely that we might have also done it this way instead. Where we just put types in order after the constructor. And there are situations where that idiom even makes sense. The difference between the first example here and what's now the second example, obviously, is that in the first example, these fields have names, and you get accessor functions for them automatically. So that's kind of nice, because when you're dealing with something that's a record, like the potential fields that you're tracking could get larger and larger over time, and like remembering which one is the fourth one and which one is the seventh one and managing this could get a little bit hairy quite quickly, right? So that's why we often prefer this record syntax if what we're dealing with is kind of like a record. But at the point here is that these two syntaxes, they're actually they overlap a lot, and so that's why down here we could make a live coder value just by following the order of the fields. And in that, if we were using that second type, it would look exactly the same, the way we would make a value in that type. But because we're using the record syntax, there's another way of specifying values in this type, and it looks like this. So let's make an imaginary live coder, Dr. Zero, who is the type is live coder. I'm gonna follow Haskell best practice and write the type before I write the thing. And now I'm going to make Dr. Zero. So I could make it like I made it below there, live coder, Dr. Zero, super collider. But I can also do this much more record syntaxy thing where I put the curly brackets again, and I do this. Which is more typing, but it's also more clear. And it has the benefit that we can change the order of these things, and that kind of thing. And as long as we fill all the fields, we'll be good. So there's a little nuance there. Like if you make a database often, and or at least in the naive way that people sometimes make databases, and you don't fill all the fields for a record, probably it won't complain, right? If you have a spreadsheet with different rows and columns, you leave some of the columns blank, you don't bother to type anything, that's probably perfectly valid as a spreadsheet. Might have problems later on, of course, but it's probably perfectly valid. But with these records that we're making, because of the strict typing here, if a field exists and it says it's a string, it has to have a string in it. If a field exists and it has a live coding language, it has to have a live coding language. So I think that what we're pointing to here is a little bit of an extra significance also to the maybe type that we looked at last time, because if it's possible that something might not be there, then probably its type should be maybe that thing, so that when you're making, you're sort of filling some kind of initial space for this thing, you can use the nothing value, and it's very clear what's supposed to have happen. So actually yesterday, let's change our definition here. We said that live coders maybe have a live coding language, but we're pretty sure they have a name, so we'll make that not optional. Just beating this dead horse a little bit, because I used the word optional there. We're saying that language is of type maybe live coding language, so like that's optional and it isn't optional in a way, right? Like it's optional for a live coder to have a language, but it's still not optional for there to be something in this space of the record. Like a nothing is a something in this case. It's not an optional value, it's a representation of optionality. you know, which is very different than what you'll see in like very more sort of like crude scripty languages where people will like, we'll put a nil value there or something like that, you know, and it's kind of like a lower level absence of something, an absence of anything that is there. When the type of our field is maybe live coding language, a nothing value doesn't represent nothingness in general, like nil does, say in JavaScript. It represents specifically the absence of a live coding language, right? That's its only interpretation. Anyway, maybe enough said about that. So let's use this different record syntax now. And we could make, like we did yesterday, we could make a bunch of live coders this way. We could go on, but I think we'll have some more stuff to dig our teeth into for the topics we're talking about today if we instead make a map of live coders. So we were working yesterday with the data.map module, and we used it to make like a map of the cool factor of live coding languages. But maybe we'll piss people off if we keep going with that, as much as we protest that our cool factors are just made up. Inevitably, someone will log into the stream and they will, you know, not have that contextual explanation, and then they'll get pissed off. So it seems too dicey to me. So maybe we'll stay away from cool factors and we'll have to think about something else. Difficulty, I don't know. That seems less controversial. But let's continue. Whatever we're going to model about live coding languages, let's use functions for that, like we did at the beginning of yesterday, because I think it's more clear. But where a good place to use a map would be in our actual database of live coders, because like that's something that could grow at any time, right? Like more live coders can join the live coding community, and then we can put them in our database of people who do live coding. So, like a map is a data structure that is good for those kind of collections of things that grow, collections of unique things that grow. So let's make a map. We'll call it the live coder map, and it'll be a map from could be a name to a live coder. Or maybe to not have there be name used twice in our system. What if we imagine there's only one live coder in any place in the world, and so it'll be a map from a location to a live coder. I mean, after all, it's literally true. We can't literally occupy the same space as each other, right? Still have more people in one city, just different GPS locations or something like that. And for simplicity's sake, let's define the type location as a synonym for string. That's a bit lazy, but it's hot in here. It's the week before the semester starts. So.
Are there supposed to be curly braces after the map location live coder?
No, I don't know why I did that. So we've made this type, and now we're going to make the thing. We saw that the data.map exports a function called fromList, which is an easy way of constructing lists. You use fromList, and then you have a list, and each item in the list is a tuple, where the first element of the tuple is the key, and the second element of the tuple is the value. Our keys are going to be locations, and our values are going to be values for live coder values. So I'll put myself here, and then I got to put a value for a live coder who has a name. I am the Dundas live coder, and we'll say that I don't have a language. And who else should we put in here? Luis, can you represent Ainsley Wood?
Mm-hmm.
Sure. Without too much loss of privacy there. Ainsleywood is large after all. And you were title cycles. Who else wants in? I'm being more careful about volunteering people here because it's got private information in it. Okay, well, I think she put her hand up first, yeah? How do we spell your name again? You know, so I'll put that. So Y-U-M-N-A? Got it. Perfect. And then Kofi, we're going to get another city from you, so. What should your language be, Yumna?
I like the nothing.
Team Nothing. And Kofi, we're going to put Montreal. What about you? I could, yeah, we could add a language. What language do you want to add? Sonic Pi, yeah, sure.
These are big languages in the music community. Sonic Pi and Tidal.
Yeah, or let's say they're big languages with different communities, or some of them have different sizes of populations. Like Super Collider's been around for a very long time, has tens of thousands of users. Tidal Cycles is more recent, but probably has at least 1,000 users, I would imagine. Sonic Pi gets used really heavily in educational context, so there's probably like many tens of thousands of students in any given year who will use it in schools, particularly in the UK, but in other places as well. All over, I think. Yeah, all over, I think. Yeah. Okay, continuing with our example here. Kofi said Sonic Pi. We added that to our live coding type, and now we can use it in our live coder value. So we've got a map. We can get rid of what we started here. I think we've done enough to test it. I'm sure we have probably done something wrong with importing something, and there'll be collisions between names, but maybe not. Let's see what happens. I'm going to reload. Oh yeah, getting this error, couldn't match expected type maybe live coding language with actual type live coding language, because same mistake we made yesterday. Our language is defined as maybe live coding language, but here in our live coder values, we're in two places we're just putting the names of languages. Because these are maybe values, they need to be just title cycles and just Sonic Pi. And actually the sort of core topics that we're talking about today have a lot to do with managing, in some ways, that confusion that we just had there. Like, we knew that Luis's language was title cycle, so what we naively did was we just put that value there. But that was wrong, according to the structure that we'd set up, because actually that value needs to be wrapped in a certain kind of context, the maybe context in this case, that we sort of forgot about, and humans are bad at exactly that kind of thing. Like, we'll make that mistake all the time. We'll kind of take the context for granted. And so the subjects that we're really focusing on today, functors, applicative style, monads, on some level they're about managing that cognitive load of the context and letting us do what we would naively like to do, which is kind of focus on the core values and have the context be kind of managed for us. That's how I look at it. So I'm going to get rid of our alternate live coder definition here, and everything we have now looks like that, and I'm hoping we're ready to go.
Question.
Yeah.
So map is great and all, but maybe you could remind us, why didn't we just define live coder map to be of type location right arrow live coder, and then all of our pairs would just,
Yeah, so
be on the
right.
left-hand side and the other sides would be on the right-hand side, and that's it.
So the question is why we wouldn't define why we're using a map here instead of say having a live coder function which goes from location to live coder, and then might look like this: live coder function Dundas equals live coder $0, nothing, etc., etc. And the reason is that we're ultimately going to be making interactive systems with this, and we have functionality with maps for updating them and making new maps from incoming information. But we're not going to make new functions normally that are compiled by the Haskell interpreter in response to incoming information. So it's like there is some difference in that sense, I think, between like a data structure like a map and a Haskell function. Like to make it, or to put it as short as possible, we think of data structures as updatable, right? Replaceable, updatable, rewritable, these kind of things. Although we could make this function on the basis of our map. Maybe that would be useful. We might end up doing something exactly like that a little bit later. So I'm going to try and load this, and sure enough it loads, and the map is already showable. So if I type live coder map, we'll get a dump of our live coder map, and it's very ugly because all of that is the auto-derived show instances for everything. Well, sure, we could write our own function called like show live coder map, that would traverse the map and print things in the way we want them to look, in a way that makes sense for these things. But let's leave that for now. Okay, so I think we've more or less obviously we've skipped over some of the topics we did yesterday, but we've arrived at kind of like the same results, a similar level of result as what we had yesterday. So now I think we can use this example to start talking about new things. So we'll move on to talking about functors. So I'm going to leave kind of a blank space here. We've already seen some behavior that speaks to this concept of the functor. We saw, I'm going to work in the terminal down here, that if we take a list, like the numbers 1, 2, 3, 4, that there's this function in the prelude map that lets us do things to everything in the list. So for instance, if I take map, whose type, let's say the type of prelude.map, whose type looks like that. A function, A to B, a list of A's gives you a list of B's. Apparently we've got two maps right now because we imported data.map, so I'm going to have to type prelude.map every time I type map. If we take prelude.map and a function like add 1 to something, and we give it the function 1, 2, 3, 4, we'll get back a list where that function has been applied to everything in the list, right? So this mapping operation, it's like we have this container of things, and we're able to take the container, do something to the things inside the container, and we get another like container. So what I want to kind of call your attention to here is that there's things that change here, and there's things that stay the same. So what changes is the value inside the container when we do this, right? The numbers in the list are what changed. But what stayed the same? The structure of the list, right? We still have a list with 4 items in it after doing that mapping operation. So we could look at this slightly differently. We could look at this in terms of values and contexts. We could look at the numbers inside the list as values of interest, and we could look at the list itself, this thing with 4 items in it, as a kind of context for those values that stays the same or works in the way it's supposed to work after our mapping operation. So this is the concept of the functor. as it's used in Haskell already. And if so, let's take a look at that in the documentation. So I'm going to look for functor using Hackage, and I get to this documentation where it tells me that the functor class is used for types that can be mapped over. And it specifies some laws that they should follow. Won't say too much about that right now. And then it provides that minimal complete definition, and the minimal complete definition for functor is this function called Fmap. And here's what Fmap looks like, its type signature. And if you look at Fmap, it looks really close to that type signature for map from the prelude that we saw, right? Like, let me bring it up in the terminal here. Type of prelude.map. See, prelude.map takes a function from A to B, a list of A's, gives you a list of B's. Fmap takes a function from A to B, and it gives you this, and you give it this type FA, and you get this type FB. So the F here and here represents the class, the type of the container. That what I just said there might not be immediately clear. We're going to come back to that quite a few times in the next hour, so don't worry. But just going back to comparing prelude.map and the functor method fmap, we can think of the f here, maybe temporarily, as like the list sign here. So almost imagine like this one, the prelude.map one. Imagine that we wrote it like this. Imagine that we said prelude.map was of type a function from A to B, and then a list of A's and a list of B's. I don't think we can actually write that. I'm not super sure, but conceptually, it's what's there. It's actually what's already there in this thing. It's like this is like a list of A's, a list of B's, and this F here could be list. It's like the F here in the type signature means any type that could be a functor. As it turns out, fmap on lists is exactly the same as map. So if we were to go back to our example a few lines before here in the terminal, and we were to do fmap instead, if we were to fmap plus 1 onto 1, 2, 3, 4, we'll get the same result. The difference between map and fmap has to do with generality. Map, prelude.map, is just for lists. So it's sort of very old, simple Haskell. Fmap is for any type that is an instance of functor, for anything which we can map into, like where we do something to the values inside a structure while preserving the structure or preserving the context. So let's explore this a little bit then by looking at the maybe type. And we'll pretend that maybe doesn't exist and that we're implementing it ourselves from scratch. So we'll call it maybe prime instead. So let's say maybe didn't exist and we had to invent it. So it would be very simple. It would be, we'd have a type called maybe. I'm going to call it maybe prime so that it doesn't conflict with the built-in one. And it would have two constructors, right? There would be a constructor just, and it would take some value. And there would be a constructor for nothing, I'll call it nothing prime, that would take some value. And because we have this type variable here, this represents a value of some type, we have to have that value in our type as well. So our type maybe prime here in that sense is different than our type live coder. Like if you have something of type live coder, that's a real type. You have a live coder. Everything about that type is specified. If you have a maybe prime, you don't yet have a complete type. You need to somehow further specify that. So a concrete type might be something like maybe live coding language, like we saw above, right? like here, where we have maybe live coding language, like the live coding language there, that becomes the A in that type, right? So that's a pretty good, that looks good for the type declaration and constructors for our maybe type. And maybe, just like it's a good habit, we should auto-derive some stuff here. Let's auto-derive show and EQ, because that makes sense, right? It makes sense to print this thing, and obviously these things can be compared to each other. You know, like basically if they're the same, then they're equal to each other. The compiler is going to have no trouble auto-deriving that. And now let's say that we want to explore the concept of making this type a functor, an instance of functor. Like, it makes sense how we would do this, right? Because the type contains this value a. So whatever that is, whatever that value contained in the just is, we should be able to do things to it to get new values, right? So if we have a just value and we do something to it, we should get another just value with the result of what we did. And if we have a nothing value and we do something to it, doesn't it intuitively make sense that that would also be a nothing value? Like if you do something to nothing, you get nothing. So because conceptually it makes sense what we would do here, there's a really good chance we can make a functor out of this. And I suppose what I'm pointing to here is that it's not inevitable that you can make a functor out of anything. There are other structures, other representations where you look at it and you're like, no, there's no way it makes sense to map over this thing. For example, the very large category of things that don't contain values. Can't map over those. There's nothing inside them to map. There's no value that's separated from a context. So looking at, I lost the page. Looking at our functor documentation, we have to implement this function. So I'm just going to make a note about it. That's our goal. So it's going to be something like instance of functor maybe where. And I'll probably repeat this, but I'm just going to draw your attention to it early on. We're saying maybe here and not maybe a. And the reason is that this type maybe, which is an incomplete type, because it doesn't have that a type specified in it, it's not a concrete type, it's not real yet. This type maybe is what becomes the f here. And as you can see from here, this is an incomplete type, right? Like the f is expected to be an incomplete type because it's going to be completed by A and completed by B in these two places here. So maybe A would actually be wrong there. But don't worry if that is not clear, because we're on the tour here. You know, we're not the maintenance. We're not the maintenance team. We're the tourists. For a few days. So our goal here is to fill in this function where we're going to take some function from A to B, f, and we're going to take values in our maybe type. So they're going to look like this. There's going to be a just something that we could pattern match for, and there's going to be a nothing that we can pattern match for. And our implementation of Fmap is just filling in those definitions. So we said that when we have a just value, we want the function to be applied to what's contained inside the just. Well, what's contained inside the just is the x. So, and we want to apply the function to it, so it would be f of x. So, and when there was a nothing, we said we just wanted to give back a nothing. So that is right and correct. Before moving on, let's just look at it a little bit in terms of types, a little bit more detail. What's the type of f here? the type of f is a to b. So any a to any b. What's the type of this whole expression in brackets? It's maybe a, right? Because f here is maybe. So this second argument of the function is maybe a. So if this is maybe a, and then this constructor just a looks like that, what's the type of this x here? It's just a, right? It's the value contained in, it's the value contained inside this just value from the maybe. So this x is of type a. Since this x is of type a, that means we can use it with our function f, which is type a of b, and that means f of x is of type b. Uh-oh, I've just discovered a mistake, right? Because f of x here then is of type b, but we need maybe b. So let's just put all of that inside a just. The expectation was that we wrapped the result in the same structure that we got the input in, right? And we didn't do that. We made that same mistake again, right? Just like I did 15 minutes ago. You know, it's like one of these like perpetual teachable moments, right? Like I was saying, like we're not good at keeping track of like values and contexts, and we'll always make these mistakes where we try to use values directly and we'll be like, oh, I forgot. It has to be wrapped in this certain way. Like that stuff is hard. We're not good at it, which is why we're making this functor instance, so that we don't have to think about that as much. We make fewer mistakes. I'm going to leave the comment there because it's probably helpful. And let's reload to check that our new type works. It's fine. And so we can try some experiments with it. Like if I do just with a prime, just prime, and I don't know, some string. Oh no, I'll use a number. Just 7 is just 7, and nothing of type maybe int. Because it's nothing prime is the value nothing. What if we try to use Fmap? So we're going to Fmap adding 10. So adding 10 is a function from a number to a number, from an int to an int, and we'll Fmap it onto the value just 5. And what we expect to get is just 15. So we're using our functor here to do something to a value that's inside of a structure and get something back that is also in that structure, the maybe structure. Well, let's test what happens when we try to Fmap plus 10 onto nothing prime. Well, we get nothing, right? There's nothing we can do to that, but the structure is preserved here. Yeah?
Can we do a list of just 5, just whatever? Be a list.
Can you say it again so I understand the...
Like, can we do the same thing to a list of like just some different numbers? Like just prime 5, just prime whatever 10, but it's in a list.
Oh, do we do an Fmap on an Fmap?
Yes. So I think the question is, can we do this with lists? And the question could be taken in several different senses. To all of those senses of the question, the answer is yes. Like with all these things, the answer, can you do it? The answer is probably yes. You can do it. Let's not do that right now. But I'll just say this: that if we start to have nested functor contexts, we'll just have to kind of keep track of at what level of the structure we're operating, right? And also, I don't think this was necessarily the sense of the question, but just also remember that lists are themselves a functor context. So I think at this point, actually, that might be a more useful thing to show. Like, see the two things we just did there? We used our new type to map a function inside of our structure, right? And now let's do it with lists instead, just a plain list. So I'm going to map plus 10 onto a list containing the number 5. So it's like the same data, but a different context or structure. But we're still using fmap, we're still using the function, nothing changes. And what do we get? This time we get a list containing 15, right? Which makes sense. Like what has happened to the value is what we'd expect from adding 10, and the structure has been preserved in the same way, but it's a different structure. And actually, I don't want to go too deep down this rabbit hole today, but if you work with the Learn You a Haskell for Great Good book, they actually make quite a lot about this concept. And there's an interpretation of lists that's very useful, where you look at lists as non-deterministic computations. So the idea is that like a list is what you get when you're not sure what the answer is. Like there's 7 different numbers in it. There's 7 possible answers to a question. So it's like a non-deterministic computation. There are other interpretations of lists as well. Just to show it, what happens if we fmap plus 10 onto an empty list, which I guess in some sense would be the equivalent of nothing in the list world? Well, we get an empty list still. So it's like, again, nothing unexpected has happened to the values. The structure, the context is preserved. So in both of these examples where we were fmapping plus 10 into 2 different kinds of functors, one that we made ourselves and the existing list type, notice how in these expressions with fmap, we don't have to like really think about how those contexts work. Like we map onto nothing and we get nothing, and we don't have to like think about how to make that happen. It's just happened for us because of using fmap. That's kind of what I've been pointing to this morning about like how this helps us reduce cognitive load. Like we don't have to think about the context as much because it's been managed already. It's being managed already by this functor type class that we're opting into. So, any questions from online, Luis? The online chat? No, we're good. No? Any questions here? Okay, so the last thing I want to say about functor is that almost anything that can be a box around something or a container for something or a context for something, these are all slightly different metaphors. Almost all of those things can be functor instances. And so if you look through the Haskell documentation, let's go back to the page for functor. So I'm going to look for hackage data.functor, not functoire, functor. After the minimal definition with fmap there, we get here a list of instances from the built-in types, and as you can see, it's a very long list, which is not surprising. And not only is it a long list, but many of the elements on this list are like very abstract instances where it's telling you that if your type already satisfies these other type classes, then it's automatically an instance of functor. So there are tons of things, a far longer list than this list of things that are already instances of functor. So fmap gets used all the time. Super, super useful. All right. So let's look at applicative, and this topic will also get referred to as applicative style, with a slightly different emphasis, or as applicative functors, which suggests a connection to the more basic topic of the functor. And there's a Haskell type class connected to this too, and it's called applicative. And here's the basic description. It says a functor with application providing operations to embed pure expressions and sequence computations and combine their results. Okay, and if we look at this first line, the class is called applicative. So what we're dealing with is any type f that might be a member of an instance of the class applicative. And here before it, we see this functor f and that double arrow. And you might remember from other things we saw, like function definitions, that the double arrow and the stuff before it are class constraints. So what this class declaration here is saying is that any type can be an instance of applicative if it implements the functions below and if it is already an instance of functor. That's what that class constraint is saying. So it's like if your type is already got functor going for it, you can also make it a member, an instance of this applicative world. And you do it by providing, like they say, an implementation of this definition pure and either one of these two things. So let's go find the, here it is, the actual official place in the documentation. Minimal complete definition is pure and one of these two things. Okay, so let's look at pure first. It has this very minimalistic description. It says lift a value. That's a very Haskell verb that sounds enigmatic and cool maybe right now, and hopefully in a couple days will just be like something that's rolling off all of our tongues, talking about lifting things. Let's not worry so much about lifting right now. Let's just take the description, take the type signature, and put it into our notes here, and start to make our type maybe an instance of applicative. So we're going about this in a kind of funny way. We're implementing it before we really understand what it's for. So bear with me. We're going to have to provide a definition for pure, and pure is going to take some value a, any value a, any type a, there's no constraint on it whatsoever, anything, and it's going to give us back an a that is wrapped in some context. So for us right now, because we're doing this with our maybe type that we made, our context is our maybe type, right? So pure for us, I'll make another note here, pure for us is going to be of type a to maybe a. That's really what we're thinking about right now. That's all we need to worry about right now. Everyone else who's writing their types, including the built-in types, they're already worrying about how to make their types part of applicative. Right now we just have to worry about making our type part of applicative. So we want to function from anything to a maybe that thing, where it's a function from a value to a value that's wrapped. So in the case of our maybe type, it's maybe it's kind of straightforward, right? We just want to put that thing in a just. Like this wouldn't make sense. Let's say x is our value. That wouldn't seem right. We're not wrapping that value x, we're throwing it away, right? But this, we're wrapping the value in a just. So that makes sense. That's correct. And in fact, if you remember the kind of very Haskell-y elegant syntaxes we were championing yesterday, you'll notice that the x is on the end of both of these expressions here. So if we want to be cute, we could do pure equals just. Do we want to be cute? I don't know. I'm going to put it back because maybe it's more important to be clear than to be cute today. Okay, so we've done half of it. The other half is we have to implement one of these two. Let's do this one because it's more straightforward. So I'm going to copy the type here. It's an infix operator. And so for us, what would those types be? Remember, we're dealing with maybe. So anywhere you see f in that type signature, it's actually our new type maybe. And so our type signature is going to be like maybe an A to B to a maybe A to a maybe B. Maybe B. So before we implement this, that type signature, it looks kind of familiar, right? Like, look at Fmap up here. So here's Fmap that we just did with a functor. So Fmap took a function A to B, and then something wrapped in F that's an A, and gives you something wrapped in F that's a B. And this one down here, this multiply in angle brackets, it also gives us something. It also gives us something wrapped, a B wrapped in something, from an A wrapped in something, and the only difference is this extra wrapping at the beginning. So the function is also wrapped. The function that we're going to apply to this wrapped thing is itself wrapped in the same kind of structure. And that's the difference between applicative and functor right there. It's that little thing. And it turns out there are many circumstances where it is useful to be able to apply a function that is itself wrapped in something, embedded in some context or structure, that it's useful to be able to apply that to things, to get other things while preserving that context or the structure. Okay, let's get, I'm sure we'll come back to that idea in a couple different ways. Let's go to implementing it. So this is an infix function, meaning that this operator goes in between our two arguments, the first one that's f a to b and the second one that's f a. So this one here is going to be, this first argument is going to be a wrapped value, a wrapped function, like a function that's wrapped in our type. So it might be just and an f. And it also might be nothing. We're going to have to consider those two possibilities. And then the second argument will be just an a value. So I'm going to use x for it. So it might be just x, or it might be nothing. And we have the same set of possibilities here. So our second thing might be a value, or it might be nothing. And we can put equal signs. These are the four possibilities. I think it's actually less than four possibilities. So it's very similar. It's going to be similar to what we saw above with functor. Like when we have a wrapped function from a to b, which is f, and we have a wrapped a, which is x, we can apply x to f, and we'll get a b, right? And I'm going to be smart this time because I've made the same mistake twice this morning, and I'm not going to fall for it a third time. We need to wrap this value again, right? Because our return type is wrapped in the context f, or as we worked out over here, our return type has to be maybe b. So if you actually have a function, you just have a function, and you just have a value for that function, it makes sense that you would get back just the result of that, right? Let's go to the second case here. What if you have a function, but you don't have a value to apply to it? What should the result of that be in the context of our maybe type? Probably nothing, right? Like that should be, that's like failure, right? It's like one of the components was missing. So we'll make it nothing. What if you don't have a function but you have a value? No. But good guess. But let's think about why just returning the value would be wrong here. So that's the idea, but we shouldn't do this. Why? Because of the type of x, right? So just this parameter, the second argument to the function, is of type maybe a. So that means that this x is, its type is A. But our return type is maybe B. So exactly. So we can't return maybe A when we're supposed to return maybe B. So that doesn't work. So is there anything that does work? There isn't, right? Like there's nothing we can do that fits that type signature. Nothing. So it's nothing. And this last one, I suppose, is the most straightforward. Like if you don't have a function and you don't have anything to apply to the function, what do you have? Well, nothing. You have nothing. So looking at this and seeing all the many times that we came to the answer nothing, we can now rewrite this, right? Let's first we can match. If you have a just and a just, you can do that application and then rewrap it. But if you have anything else, then you have nothing. So ultimately, there's our simpler implementation of applicative for our maybe type. So I'm going to reload that. Oh. Error, line 44. Ah, yes. Yeah, exactly. F of x needs to be in brackets because otherwise what happens is it tries to apply x to the just function because it's a function, and just doesn't need a third argument. So that doesn't work. And if you look closely at the error message, it's kind of giving us a clue, right? And it's typically excessively verbose Haskell way. Like it says the function just is applied to 2 arguments, but its type, and here we'll give it all the gory details, has only 1. So yeah, we need to put this in brackets. Now we're good. And so now we can use these operators, right? So if we type pure 7 and we tell it that this needs to be a maybe int, we'll get the value just 7. Not really surprising. If we, let's try to use this operator here, this application operator. So let's take a function, a function that works on numbers, like plus 10 is what we did before, and let's apply it to some number, like just 5, and we get just 15. So that's very similar to, again, to what we were doing a second ago with Fmap, except now the function is already wrapped in a maybe. So what if the function didn't exist for some reason? Like, what if, so imagine that the function had to be gotten from somewhere, like I don't know, a database process. Like you had to do a database lookup to get this function that is going to be applied to this data, but oh no, the database is down. So the function, sorry, it's not there. What are we going to do? So then that function is going to be nothing instead. And we're going to try to apply it to our data, and we're going to get nothing instead. So see, it's like the context is preserved. Like something in the context, in my imaginary example, it was the failure of the database. That contextual piece influenced what happened to the data. But we didn't have to think too much about it. We were just like, oh, the function's missing. There's some consequences for that. The consequences of that information about the context were managed for us in some way. So the applicative style is really useful because often what you'll be doing is you'll be chaining together lots of things that have contextual information attached to them in some way. And if you had to like pattern match on all of these conditions, and like if it's just this and nothing that and just this and nothing that but nothing this and just that, like the code explodes and becomes this like incomprehensible mess. But if those relations between, let's say, the presence and absence of things that you require, in the case of maybe, if they're managed by the type class, then often the definitions are much simpler and our brains don't explode. So we have provided a minimal definition of applicative for our maybe class, and because of that, we get a bunch of other nice stuff for free. So for example, if we go back to the documentation, one of the really useful things, if I can find it in here, well, I don't know where it is, but let's look at it here. So if we look at the type of this operator that looks kind of like the applicative application operator, but it's got a $sign in it instead. If we look at the type of that, sorry, it's got to be in brackets. This is just a synonym for Fmap. That's why I didn't find it in the applicative documentation, because it's in the functor documentation. So nothing about this, if you look at the bottom of my terminal here, nothing about that line says anything about applicative. But let's read this a slightly different way than we did a second ago. It's like if f is some kind of functor, this function, which is just another name for Fmap, by the way, this function takes a function from A to B and gives you a function from a wrapped A to a wrapped B. So there's two ways of talking about this, right? Let me say this again. Like a second ago we said, well, if you have a function from A to B and a wrapped A, it gives you a wrapped B. But that is exactly the same thing as saying if you got a function from A to B, then you get a function from a wrapped A to a wrapped B. Those two things are equivalent in Haskell. So now we're kind of emphasizing that second one. See, what this lets us do is it lets us take a function from A to B and turn it into like a wrapped function from A to B. So our example up here, where we're applying 10, let's say our function 10, adding 10, we want to apply it to a wrapped value. We can use that. Oh, sorry. We get the same result. And if we take that same function and we apply nothing to it, of course, we'll get nothing. So what about if we had a function that takes two? This is now where applicative starts to get cool and really elegant in actual projects. What if we had a function that needs two numbers, like plus? Well, we can do this. And chain these things together. And because of the semantics of our maybe type, if any one of those things fails, i.e. is nothing, the result will be nothing. Just in case anyone doesn't believe me, let's do it. Oh, that's nothing. But this is also nothing.
So if I have a function of many arguments and I want to lift it to behave on containers, I first use the dollar
Yeah.
in angle brackets, and then everything else I would use the star in angle brackets.
Yeah. Yeah. That's a very practical way of describing it. I'll repeat it for the benefit of the internet. If you have a function that has many arguments and you want to lift it to work in this context, such as maybe, you can use it before the angle $sign operator to lift it into that context, and then have each of the contextually wrapped parameters to that function separated by the multiplication angle bracket operator. Let's make an example of that. We'll make a lambda function that takes 3 arguments. So x, y, and z are the arguments for this function. And it takes x squared and adds y and subtracts z. It's the scientific formula for how long a live coding artist will live, based on I'm not sure what. So that's a function. And now it needs to consume 3 values. But let's say we don't know if these values exist or not. They're unreliable in some sense. So we're going to wrap them in a maybe. So, okay, let's give it like 10 for this one, 20 for this one, and 30 for this one. We get our answer. But if instead one of those had failed, oh, wrong nothing. We need our special nothing. Then we get nothing. So there's, I know I'm beating a dead horse here, but like what we're seeing here are strategies for separating the values in some calculation from the structure or context of it, right? Okay. We've been going for about an hour. Should we take a little bit of a break before continuing with monads? Let's take a 9-minute break, and we'll start again at 11:20. I think this is a 2-coffee morning.
Oh, you're right. Coffee's good. How goes it? Sorry?
Go to editor, because I don't have an editor set up. That's a type of.
Oh, I did that. Yesterday, that's what I was doing. I was using Notepad. But the thing is that, like, I didn't, like, you know how Haskell is so, I would get errors. Oh, you could get GN. That's what I was today.
Oh, yeah, it has coding?
Yeah. But also, it also has, because I was using Notepad++, but Notepad++ only does you see the things in red, but it doesn't show me the things in green.
Oh.
So, like, gedit already has the green part.
Right. Are you running a VM?
No.
Straight.
Well, those are just, whatever. I think that'll work. But yeah, 'cause that's what he was using. I'm like, how do I get the red? And then I realized that because due to the terms, and you're doing a PhD, I think you said before, right?
Yeah.
What are you doing a PhD in?
Not a programming,
Okay.
but I use McMaster for that. So my Haskell is very rusty. And
That's the first time. I've seen Haskell before, but it's one of those things that like after I went to work, because it's like it's very different. I also come from like a more traditional background. That's like how Java, Python. Like
Yeah.
I never learned Python, but it's not hard to read. Like once you know a couple languages, you can you might not know what it does, but you can read it. Haskell code is always one of the ones that I see it, and I'm like,
What is it?
I can't even read.
Sure. You're doing.
I'm not even. I might be doing maybe next year.
Oh.
I'm from Montreal. I just can't click. I want to do the I went to the live coding thing.
Oh.
Like I don't know if you expect this. So live coding is basically on the fly paragraph of programming. So you know how there's graphical programming, and I don't know if you're familiar with processing thing. Processing which is like for graphical stuff. Well, this one is more for audio stuff.
Okay.
So, and then people in Israel tend to build their own languages derived of others. So, let me just show you. You seen Ruby before?
Yeah.
Okay. So, like ever since the update, I can't search, but I have one. And this is like, I'm more interested in this type of computing than normal. It's this, in the end of the day, it's all coded, but it's just a different output. So the guy who built this built it upon Ruby.
Okay.
And then the reason why he does it because he builds languages and a lot of like the languages that are, or libraries that are built, a lot of people use Haskell.
Okay.
And I think, and it's really because of the strong type, right? Because if you want sounds, you want like, if you type something, to be able to get the same sound and to be able to switch the sound, you want to be able to go back easily. Whereas in like, you know, object oriented, like, you can have X, but that X might not be the same X 10 down.
Yeah, exactly.
Whereas this one, if you see it once, you already know that you just follow. So like, and that's what I really appreciate about functional. Like I started realizing debugging is easy. Easier.
Yeah, it's different, yeah.
But you know what I mean?
Yeah.
You gotta find your commas and stuff.
True.
Like, so you see, like, this is one of them. They use, so the names you see, those are all different languages and environments. It's not like it is.
Yeah.
It is, and that's. Oh yeah, you got your PhD. So no, but no. But I want to concept that if you talk to non-coders, they don't use that word like because I've been explaining to people that don't know computer science.
Right.
So, but no, you're right. Everything it is a domain because a DSL. Someone was saying like the difference between a library and a DSL is just a DSL. It's a more complicated library, but at the end of the day, it is the library just complex to a point that this is built off of Ruby, right? But you change the person and all that stuff.
Yeah. Okay. That's pretty cool. Interesting.
Yeah, that's the Ruby one. Let me go back. But then people build it off all different types. So there's a lot of people that build off JavaScript, but then again, to be honest, who doesn't build off JavaScript?
Yes.
I feel like everyone has built something off JavaScript. JavaScript is a punchy bag. No, but like honestly, like the guy built it supposedly in 11 days. You ever heard that? He built it in 11 days. Supposedly, that's why it has no like. It's a purely made language, but if you build it in 11 days, it really like the internet is trash because of JavaScript. Because no one knows proper JavaScript. Like, is there even such thing as proper JavaScript coding?
Yeah, that's the convention.
Who follows the convention? There.
That's
You see this? This doesn't make sense, but this is a language that someone built off Pi. He calls it an environment, but it's really more like parsing. It's really straight, like one, but you could use using processing before. It's a Java, but it's not. It's like graphical. It's based on Java.
Okay.
The only reason why you might not is just because you don't have the static void main. Because it's meant for artists, so like the hello world in this is really just making like a little box. That's part of like the paradigm.
Snakes are like quite a different level. Like snakes are a certain creature.
One guy that built
But they're still
because your friend there was
snakes.
saying,
Your
he's like, I didn't know that this whole other world of computer
Do you
science.
think they're interesting creatures, or do you think they're absolutely disgusting?
But
What's the benefit of
There-
using this way?
You would or you wouldn't?
well, the way he said it,
My brother
is that just
wanted
you-
a
because
snake
when
as a
you
pet.
have the-
At some point,
you know,
like-
Shell Rock,
It's
like,
not
freestyle,
big though. That's
like
wrong.
audience.
so
and you know
cute,
when you
and I'm
do
like,
when
where?
No, they're not.
But you have to have goals and like
I think he said like a dead rat or
for some people
something.
that you have to do synthesis and they
I have a friend who
do
says the same
that's
thing.
very good.
Whenever I mention
Audio
snakes, because I'm
basically way
completely fucked.
so some of the
They're
programs like
my
super
biggest fear.
lighter,
Whenever I say
audio
snakes,
audio synthesis.
she's like, oh, they're so,
But also,
so cute. Like,
you know how we're into the world of data visualization?
And you know how
One of the things that is like the human
we
ear
have
is very
snakes.
receptive to different
And
tones.
like, it's
So
like
there's
you
also
walk
another
through
field
it,
emerging
and then
in the
you
world
go
of
on
data
to the other
science
side.
called data
I remember
sonification.
a few years ago when we
So
went,
and machine
I
learning
was
is
so
also
afraid of
machine
going in
learning.
there. And then
Because
when we
we're
went in
running
there,
this,
I
one year you're only thinking
closed
music,
my
but
eyes,
remember sounds all around us.
I
And
didn't
being
look
able to
anything
tell the sounds is a
It was
very,
like-
like he doesn't go all the time, but think about like, what we're talking about, how a computer can see. What if a computer could hear well, or like, this thing sounds, but there's more sounds than there is. Yes. Is there more sounds than color?
Do you think that would have
Arguably.
like a lot of time?
Because remember, human eye is reliable, but it's also unreliable. So a lot of people have color and different, but like you can hear tonal differences. So, but that's another area because I like data science, and that's another area that I like. But for them, it's like they would like the, so they have like a background history of that, or like they would perform like 20 people share like online text editor that they made, and 20 people would be typing code and producing music that is like they're like, it's not like pop music, it's like sometimes noise, sometimes like mismatch, because it's improv. So you could do a lot of things in it.
I'm done all
She's
of
doing
that.
visual.
You already
That's what she do. She likes building like many languages.
She just, you know, like without her.
She's the funniest though.
Yeah, without her, that's what she's without her, they would all be like,
And trust me, I came from like different backgrounds. Like, huh? And then was like, we build languages. And I'm like, why? And then I tried to look. I was like,
But
no,
Gina
like,
is weird
how
too.
did it use like, I did it use like, isn't that common in computer stuff? Like, no one is just nice builder.
that doesn't change the fact she's the best. No, I don't know if she's the best.
I like some music. But like,
I really
That's why
Haskell
this is my
also
third
like-
time coming down with them. I'm gonna be composed. So I just like.
Yeah, same.
So I think I really Santiago and Bogo.
Does he not?
I'm very
I
bored.
know,
I'm very bored of like the way he gets excited
How
about
about
it.
it?
Between boil and boil.
Okay, so we're back. Sorry, I'm a couple minutes late there. Okay, the third of our three rather challenging topics for this morning, monads. So just like we did with applicative, let's work from the official requirements of this third type class, monad. So I'm going to look for monad on Hackage. It's going to take me to the control monad module. And somewhere down here, here it is. So there's a class monad, where we can make our types instances of this class, provided that they are already instances of applicative. So you see the pattern here, like between these three type classes. Like something could be a functor. If it was a functor, we could maybe also make it applicative. If it was we can make it applicative, we can probably also make it a monad. And in practice, you often see things that are just all three of these things. And I was just talking with Jamie about this. I think the reason why you see these the types that are typically instances of all three of these things is that in some sense it's just a matter of notational convenience which of these three styles you're using. We'll come back So we'll skip down to the minimal complete definition. And the minimal complete definition for monad is you just have to provide this operator, whose type is right here. Let's read the description. It says, sequentially compose two actions, passing any value produced by the first as an argument to the second. So all I want to flag for your attention here is this word action, because sometimes when things are wrapped in a type that is a monad, we talk about that as an action, as a monadic action. That's often the vocabulary around for it. It's not really saying anything different than what I've been saying in this, 10 minutes ago when I was talking about wrapped values. Like an action is a wrapped value. Just a different way of talking about the same thing. And although the return type is not considered part of the minimal complete definition, it's really useful, so we should probably do that as well. So I'm just going to grab that type signature, copy it in. I'm going to grab the return type signature and copy it in, and just comment that out. Those are notes for us. And I'm going to start writing my monad instance. Instance of monad, maybe, where. And I'm going to do return first. So if you look at return, its type signature is some value A to a wrapped value A. So the M here in these type signatures is just like the F in our applicative type signatures. It's just a reference to the wrapping structure. And for us, all of the M's here are again going to be our type, maybe. So the type for return for us is actually A to maybe A. Well, we've already done that, haven't we? Like when we did applicative, we made this function pure that just takes a value and wraps it in a just. So return equals pure. They are the same thing. They are different names for the same concept. And that's actually why return is not part of the minimal complete definition. Because, as we saw above, for something to be in monad, it has to be in applicative as well, which means pure already exists, which means they can make a default definition of return that uses pure. So that all being said, let's delete our return equals pure because we don't actually need it. Or maybe let's leave it in a comment, we'll leave it in there as a comment to emphasize the commonality between applicative and monad. Okay, now we get to the more substantial one, this operator, like that. And this has a name. It's called bind. This operator here is called bind. And after we've had a bit more experience with it, it will make sense, I hope, why. I'm going to take this type signature for bind, and I'm going to get rid of that beginning part, which might be confusing, and just leave it at there. And let's look at this type signature. So bind takes a wrapped value, like an A in some structure, an A in some context, and it takes a function that goes from an A with no context to a B in some context. So the type signature of this function that you provide, that's key to understanding what's different and unique about this monad idea. Like this function, this here is a function from a pure value, from a value that has no context, to another value that does have some context M. And what bind does is, given a wrapped value A and a function from an unwrapped value A to a wrapped value B, it gives you the wrapped value B. So we'll come at this several times in the next few minutes, and hopefully it'll make more sense. But let's say just this at the outset, that this type signature is potentially useful for us for reducing cognitive load, making things simpler, because it lets us write a function that produces a wrapped value working with an unwrapped value, which is going to be simpler for us, right? because when we write that function, the value a is unwrapped. We don't have to unwrap it ourselves. We don't have to match all these special cases for what could happen, right? Okay, let's try to write it. So we have the bind operator. It's like all those other ones, it's infix, meaning one of the arguments comes before, one of them comes after. And the thing before it is going to be a wrapped value. So in our type, our wrapped value might be just x, or it might be nothing. Those are the two possibilities. And then the second argument is a function from a to m to mb. So it's a function. So let's use the letter f to represent it. And now we have to provide the definition. Let's do nothing first, because it'll be easier. If we get nothing, and we have a function that's supposed to consume the value that was contained in that structure, but we got nothing, what should we give back? Nothing, right? Like what can we give back? Obviously nothing. So there we go, nothing. If we actually get a value wrapped in a structure, a just, and we get a function, well, we're gonna give back some wrapped value, right? What's the value that we give back going to be? It's going to be f of x, but we haven't thought quite straight about this here. If you look at f is of type a to mb. In other words, f is already a function that, given a value of type a, gives you a wrapped value b. So we don't need the just here, right? Because f of x is already maybe b. Like to make this clear, let's write this type signature out more concretely. So all our m's here are maybe. So from a maybe a to a function from a to a maybe b to a maybe b. So this is this here that I'm highlighting, a to maybe b, that's the type of f in these expressions. So f of x, so f with an a applied to it, is already maybe b. So it's already the correct return type. So all we need here is f of x. And that's it. We're done for our implementation. So let's try to use this now. Well, let's check that we're correct first of all by loading it. Yeah, we are. So let's try to use it a little bit. Okay, well, so we can check that if we try return 7 of type maybe int, we get just 7. So that worked. And now let's try to use bind. So we're going to need a pure value. We're going to need a value, a wrapped value. So maybe it could be a number, like just 5. Keep going with our previous example. So that's a number. I'll put it in brackets. A number wrapped in our structure. And we're going to bind that to a function that takes a pure number, just takes a number, an a, and returns a wrapped value. So I'll do this as a lambda function. So a function x, where what we return is just x plus 10. And that's it. So we've provided a wrapped value, and we've provided a function from an unwrapped value to a wrapped value. Bind should put these two things together and give us the resulting value. But what happens if there's nothing? We are trying to use this function with an unreliable data source, let's imagine. And unfortunately, that value that we're going to add to it's just not there. It's not there. What happens? Oh, sorry, I used the wrong nothing. Nothing prime. Well, we get nothing. That piece of structure or context propagates through our expression in a meaningful way. Yeah.
So in the above example, if you took out that just prime and then moved the function to the very beginning and then put a angle bracket multiplication sign, it should still work. And you should still get nothing prime, right?
If I understand the question correctly, I think you're asking about rewriting this in the applicative style. Yeah, so like in an applicative setting, this might look like the function would be at the beginning, probably instead, and it would be x plus 10. Oh, sorry, it would just be plus 10, and we might lift that into the applicative style and apply it to our nothing value. And in the functor setting, it would look like this. It's almost the same thing. So versus Fmap 10 onto just 7. So it's actually really useful to go between all these little different variations of the things that are, one is functor, one is applicative, is monad, because they have so much in common. Like it's the difference, right, is just what is wrapped in a structure and what isn't wrapped in a structure. Like with Fmap, where's our Fmap example here? Here's the type signature for Fmap. With Fmap, our function isn't wrapped at all. It's just a normal pure function from some A to some B. But our values A and B are wrapped. With applicative, everything is wrapped in some structure. The function is wrapped. What we're going to apply to the function is wrapped. The result value is wrapped. With monad, really it's the signature of bind is what matters. The input value is wrapped. The function takes unwrapped input but produces wrapped output, and the output is wrapped, is in some structure. And this, again, is useful because often we are going to be making things where everything is wrapped in some structure, but it would be so nice if we were able to ignore that temporarily and just use the values as if they weren't embedded in a complex structure. And so being able to write functions that have this monadic, have this signature, A to MB, is super useful. It helps us, it reduces our cognitive load in a way. This, I think, is the time to talk about a really common way that monads are used in Haskell called the do notation. So if a type is in a monad, like if it's an instance of monad, then we can use this special Haskell notation called do with it to sequence together, to tie together a bunch of these monadic calculations. So let's say that we have some value test, and it's in our maybe type, and it returns some number that we're interested in, but maybe it doesn't. Like test is something that gives us a number we're interested in, except maybe that it doesn't because it fails or something like that. So that's what I've expressed by that type there, right? And again, I've been a good Haskell programmer, and I've done the type first, and I've thought about it and thought about what it means. So test is something that probably gives us an int, but might not. So it's an int, but it's an int with the structure of uncertainty around it. So we're going to use this do notation and define test by saying test equals do, and then I'm going to go and I'm going to indent, and everything that's inside this do expression I'm going to indent to the same amount. And well, I'm just going to do something and then we'll talk about it. So imagine 42 is a number that we might not get. We're going to get it there, but imagine that we might not get it. And imagine that y is something else that we might not get. Actually, I'm going to use the same numbers we were using before, 5 and 10. So x, it's like x is some value that we may or may not get. Y is some value that we may or may not get. And what we want to return is the sum of these two numbers, both of which we might not get. So this is a normal use of the do notation. And so before talking about how it works, let's just do some tests on it. So I'm going to save it and reload, and we're all good. And I'm going to evaluate test and see what we get. We get just 15. So we had a number that was wrapped in some context. We had another number that was wrapped in some context. And we were able to sum them and also get that also wrapped in the same kind of context. And the way the context has been preserved or maintained is meaningful. What about if one of those numbers wasn't there? So we're trying to add something to nothing. Well, we expected this should fail, right? We should get nothing. So we'll reload. Sure enough, we get nothing. Well, what if both of them are nothing? Or what if the other one was nothing? Also nothing. And maybe we can just leave it on faith that if both are nothing, you get nothing. So we have these, you can think of this line here, the x line, think of it as a computation that produces a maybe int. So that int might be there or might not. It's an int with this structure around it. And think of this other line as another one of those things as well. A computation that might produce something or might not. And then here, we're putting them together and returning it. So there's a couple things to say about this. And I think the most important thing is this. Like this expression here, x plus y, like we're just adding x and y together like they're normal numbers. Right? Like we're not treating x and y as if they're maybe values, but it's working. Right? That's the magic of monads and the magic of the do notation. Like let's imagine we didn't have monads and we didn't have the do notation and we tried to add together two maybe numbers. So like we tried to do this, just 5 plus just 10. Doesn't work. And without going into the details, perhaps we can see intuitively why it doesn't work. Like addition works on simple numbers. Addition doesn't work on complex structures of presence and absence. Like what does that even mean, right? But we're able to give a meaning to that in a way that's not too cognitively loading because of monads and the do notation. Right? So when you use the do notation, I'll just mention this just kind of by the way, what happens is it gets translated to a sequence of these bind operations. So let's see if I can, I'm not 100% sure if I'm doing this right because it's not something I think about often, but I believe that our test gets translated to something like this behind the scenes. It's like, I'll translate what's there. It's like nothing bound to a lambda function whose argument is x that, let me see if I'm doing this right. X in I'm not sure if I'm doing this right. Nothing bound to a function x where just 10 is bound to a lambda function whose argument is y that returns x plus y. And then the brackets are like that. So that bind operation, whose magic we saw a second, I think I've got that right. Not 100% sure. That's why these live streams are ephemeral and are going to be deleted later, in case I'm making horrible mistakes. I think it's something like that. Anyway, long story short, that bind operation, whose magic I think I've understood at some level already, the do notation, it gets translated into a sequence of those bind operations. And so what that means is that realistically, like, this is a maybe int, but x is just an int, right? So we can look at this operator in the do notation, that backwards arrow. We can look at it almost like it's extracting the value contained inside our wrapper type. It's not really extracting it. It's like extracting it only to put something back in the wrapped type. So it's like we're in the wrapped type the whole time, but it's like we get to pretend that we're not in it for a moment, right? Actually, we get to pretend that we're not in it for all of the subsequent expressions. So anytime we use x after this line, x will just be an int, not a maybe int. And that's what lets us, y will just be an int, not a maybe int. And that's what lets us just do x plus y here, which is so much easier than figuring out all the possible combinations of nothings and justs that are happening here. And, perhaps this goes without saying, but like, we're dealing with a really simple monad here. Like, we're dealing with the maybe monad here. Like, that's a very simple, obvious monad. Like, when things are all just, you give back justs. When things are nothings, you give back nothings. It's pretty obvious, right? But we might have a much more complicated one for some specific project or thing where the nuances of the context are quite detailed, right? Even so, the do notation and monads are going to let us push some of that away and deal with pure values and simple operations to a greater extent. So super, 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 super useful. So I think what we've done here is we've developed maybe from scratch as an instance of functor, applicative, and monad, which is a fun exercise, but it's not actually something we need to do because the actual maybe type already does all this stuff. So just to prove that, let's take off the primes here. So now we're using the built-in maybe, the built-in nothing, and the built-in just. And when we reload it, it's still happy, and test gives us the result that we expect, because everything we just implemented is just we're just reinventing the wheel, basically. That's how maybe already works. Okay, last topic. So there are lots of these things that could be functor, applicative, monadic contexts. It's super, super common. That's why it's so useful. And later in the week, we'll meet some more complicated ones to do with the web browser space and to do with doing programming with Haskell in the web browser. But a really common context that can be managed with these tools is just input-output, or I/O for short. So before getting into this, I want to point out that everything we've done to this point in this school with Haskell has been working with what we might call pure values. Like nothing, or let me say that a different way. Nothing that we've done so far has depended in any way on interactive input and output. Like we said from our very first exercise at the beginning of yesterday, we said x equals 7. X is just 7. You don't need to press a key for x equals 7. You don't need to ask the user. You don't need to query a sensor. X is just 7. It's always going to be 7. There's no input or output there. So now we're starting to get some input and output. And so let's look at the type of some useful functions. So one function for input and output is called putStringLine. And let's look at its type. Now, isn't that type interesting, given our preceding discussion of monads? Like putStringLine is a function that takes one argument to produce a result. The argument is a pure value. It's just a string. It's just an A. But the result is a type involving a type variable. And so we've got this type constructor IO followed by the variable unit. So at this point, I should explain a little bit about this unit thing here. This unit here, these double brackets, it's called unit, and it's a type in Haskell. It's the most boring type in existence. It's the type whose only value is unit. So it's a type that only has one value, so therefore it contains no information. For example, this is that, and that is the only allowable value in that type. If we ask for the type of this, we'll also get that. So it's a type that says nothing. It's a type, an empty type. And there are various reasons why that's useful. And one of them is working with monadic computations. Because we might want to have something, for example, that does something to the context, but which doesn't actually have a value, right? Like, let's think about lists, for example. What if we had a function that you give it a list, and it throws away half the elements in the list? Well, that's not a bad example. That's changing the values, actually. What about a function that takes a just value and turns it into a nothing? You're not actually interested in what was in the just, but you're changing the structure. I don't know if these are great examples. Anyway, suffice it to say, these double brackets are the type unit. It's the type whose only value is itself unit. And so what this type for putStringLine means is we have a function that we give it a string, and it's going to give us something in this IO type, in this IO structure, in this monadic IO context that doesn't have any value of interest. And the reason why it doesn't have any value of interest is this is just something for spitting text out on the screen. So you don't expect to get something back from that. There is no value of interest in this. But there's still a structure, see? There's still a context. It's doing something to the computer. It's doing input-output. It's making something happening. That's a structure or a box or a context for this computation. It just doesn't have anything inside of it that we care about, that we need to do anything with. So that's why its type is IO unit. Well, let's look at another type, getLine. So getLine, the type is IO space string. And so again, we recognize here a wrapped value, right? A string is wrapped in an IO structure or context. And what is getLine? What is getLine? getLine is a definition that gives you an IO context for producing a string value. Well, let's write a simple IO program to test it. And maybe some of this will start to become clearer. So test2 is going to be an IO program. And it's not going to produce anything of interest. So it's going to be IO unit. We don't intend for this IO structure to ultimately contain a value that we're interested in. And we're going to use the do notation. And let's print a prompt. Please enter a string so I can repeat it. And we're going to use getLine to get that string. And then we're going to use putStringLine to print it again. And then just because we are Canadian and we're oh so polite, we're going to say thank you. So let's run it. And I'm going to run this by evaluating it. So test2 already exists. Test2 is an I/O structure that returns no value of interest, that returns unit. It already exists. When I evaluate it, the default behavior of the Haskell interpreter is to take that I/O structure and to run it, to execute it. So this is something a little bit different than what I'm flagging here is that this is a little bit different, sort of secretly behind the scenes, a little bit different than the other things we've been evaluating at the terminal so far. Like when we evaluate the number 7, you know, it's the interpreter is going and figuring out what that thing is, and it's printing it for us. But when we evaluate test2, it's going and figuring out what test2 is, and then it's running that thing because it's a program and not simply a value. It's an I/O program. Test2, please enter a string so I can repeat it. I'm going to be even more polite. I am happy to oblige your reasonable request. And it repeats it for us, and it says thank you. Yeah.
So our other functions, none of our other functions at the terminal made the terminal wait.
Right.
But getLine makes it wait.
Exactly, yeah.
Can we define, like how is getLine telling the terminal to wait?
Yeah, so the question so the question for people on the internet is that everything we've done so far, there's been no waiting. We've evaluated things and we get the result right away. And this time, when we evaluated test2, there was it waited for us to enter the input, and then later gave us stuff later. And so it seems like there's this element of delay that is entered. It wasn't there before. So that's a really good question because it gets to the heart of the matter here, actually. Actually, we didn't have to wait for test2. Test2 is a program. And when we evaluated it, we got that program. We have the program. And we're not evaluating it anymore. Like, we've got the program. And the program is run. And the waiting is part of the running of the program. It's part of our experience of the running of the program.
Okay.
Maybe that's probably the best answer I can give. The I/O program, test2, existed from the moment that we evaluated it. It was all there. And then it got run, so we experienced it. It's probably useful here to look a little bit at the types of these things. So putStringLine, again, is of type string to IO unit. So that means this expression here, which is putStringLine plus a string, the type of this is IO unit. GetLine. GetLine is of type IO string. So here, getLine is of type IO string. I'm just repeating the definition there. And X is of type, this is a key question. What's the type of X? Everywhere it appears in this expression. String, exactly. Because this thing in the monadic notation is a kind of shortcut for writing a lambda function that is then used with bind and effectively allows us to extract the pure value from inside the structure. So x here is of type string for the remainder of that expression, of this do expression, do notation. So put string line is of type string to IO, and that works, right? Because x is of type string. If x was of type IO string, this wouldn't work, right? Like, let's try to do that. What if we try to do put string line, get line? Now, like, I'm deliberately making a mistake here, right? Get line is of type IO string, and I'm using it where string is expected. That ain't going to work. And we're going to get an error message that says exactly that. Couldn't match type IO string with string, basically. List of char.
Oh, but we can flip them around and put bind in the middle.
So the question is, can we flip them around and put bind in the middle? And yes, the answer is right. We certainly can. Get line, put string line, works.
Why does that work? I didn't think it would.
The person asking the question says they're suggesting it, but they didn't think it would actually work. And so the question is, why does it work?
Because the first one, get line, is a function, and bind wants a monadic value. Oh, get line isn't a function.
Yeah, so
Get line
let's
is a monadic value.
let's put it up here so we can type about this a little bit
That's
easy.
fine.
Whoops, wrong one. I'll just type it again. So get line is of type IO string.
Which is not a function.
Put string line is of type string to IO unit, an IO computation, an IO structure that doesn't have any value we're interested in. And when we bind them together, so the type of bind is some monadic value, a function from a pure value to a monadic value returns the monadic value. So when this MA is IO string, then this is string to IO unit, and this is IO unit. So put together, it's IO unit. Put together, it's just an IO program that we can run, and that doesn't give us any interesting value back, but it still does something. So, like, let's take this moment to look at some of the different monadic contexts we've looked at. So we've seen that a list, i.e. 1, 2, 3, 4, can be seen as one of these contexts, right? And what's the context here? There may be 0 or more values, right? We might also see that as non-deterministic computation, like multiple possibilities. There's stuff in the list, or there might not be. That's a kind of context. We saw that maybe is a kind of context, a kind of box or container or setting as well. And here the context is there might be one thing or not. Or we might also see that as success with a value versus silent failure. And now we're seeing that IO is another such context. And here, the context is that we might interact with the user via, keyboard, GUI, file system, etc. See, in all three of those contexts, we can separate to some extent the context from the values we're getting out of it. And being able to do that helps us think about things and design things, because we're just better at dealing with pure values than dealing with context. Dealing with context is hard work. So it's nice to be able to do it every now and then forget about it, and just go on to dealing with simpler values for a while. Otherwise, we'd probably we'd go nuts like doing this stuff. So there's more you can learn about I/O. I don't really want to go too much into it now because it can just be kind of tedious. Like, here's how you get a character, here's how you get a line, here's how you read a file, blah 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 blah. It's all kind of tedious. But if you look in the Learn You a Haskell for Great Good book, there's a chapter on I/O, and it goes through it in a very straightforward way, what many of the possibilities are. So it's useful for that. I think the last thing I want to do this morning is just show another example, much more briefly, another example of something that is a monad, and that's either. So yesterday we looked at the either type, and we saw that either is something that can either be a left value or a right value of particular types. And that, moreover, there's a common interpretation where the left value is some kind of failure and the right value is some kind of success. We talked a second ago about maybe, potential interpretation of maybe being that it's a success with a value versus a silent failure. The silent failure part there, that's kind of dodgy. Like if you're making a tiny system, okay, fine, whatever. But if you're making a big system that you're going to have to debug and maintain over many years, for example, like the estuary project that we're working on here, it's a growing piece of software, very complicated. Managing that and maintaining it is like a going concern. It's not just a day's work. Silent failure is not so good in those situations because things fail and you have no idea what failed because all you get is a nothing, right? Error messages would be really nice when things fail. So we really want to do things probably often more with either. And in fact, on Thursday we'll see there's an even better mechanism above either, but based on it, called except. But it's an example of something called a monad transformer. But we'll come to that later. I'm just kind of sort of charting a direction here. So let's talk about either. So big use of either is some kind of computation that might succeed or it might fail, but if it fails, we want to know why. So let's go here. Let's go up to our test example here, and let's make test 3. And let's make it an either type. Let's say it's either going to be an int, that'll be the right value, that's our success value, or it's going to be something that tells us about our failure. If we were really doing this in a hardcore way, we might make our own type for representing failure. So in a real system, you'll see that, like types that represent failure in robust ways. Since it's the week before semester, and we've done a lot of heavy stuff today, let's be lazy and just use a string. So we'll just have a text message that tells you how you failed. Why do I keep beating up on strings in this school? And why do I call them lazy and all that? It's because in many circumstances, like they're easy to put in. The type already exists. We don't have to do any work. But because it can be any valid text, it's super easy to put invalid things in there. Like there's no safety in strings, basically. So really, the only good use of a string should probably be like in some dictionary somewhere, where you're just you're kind of like you've got the things that are going to be displayed, and maybe the dictionary has different languages in it and stuff like that for internationalization. Everywhere else, a string is kind of maybe a liability because it can be anything, and the compiler isn't going to tell you that your text is invalid. Anyway, we'll throw caution to the wind and use strings here. So I'm going to rewrite test above using either instead, and I'm going to use the do notation. And the reason I can use the do notation is because either A is an instance of monad. So before I do this, let me just, there's more discussion of this in the Learn You a Haskell for Great Good book, but it's not an accident here that I said either A is an instance of monad. I didn't say either. I said either A is an instance of monad. Because remember, our monads, our structures that we're using in this monadic way, or this applicative way, or this functor way, they always have that type signature where it's like MA, like a structure and a pure value. So here, in our example, int is our pure value of interest. So our structure is either string, not either. In other words, it's either A. And a consequence of that is that the string part of this either is not one of our values of interest. It's part of the structure, not part of the values. So, for example, to make this most concrete, when we use return, the same thing as pure, in the either string monad, that'll be something that has to return an int in this case. It won't have anything to do with that string in the either there. Won't be able to touch that. Okay, so let's try this same example. So x, and let's say we have a successful 5 here, and we also have a successful extraction of a 10 from some other process. And now we want to return the sum of them. That looks good. Oh, we have some dangling stuff somewhere here. There's a bind operator on line 89. Where is? Oh yeah, it's all this stuff. I'll just comment all this out. Go back to where our new thing was. We're good. Test 3 is now right 15 instead of just 15. It's a successful 15. But now, because we're using either string instead of maybe as our monadic context or structure, if we want to make something fail, instead of putting nothing, we can put left. Sorry, this value isn't available. And when I reload it and evaluate test 3, now I get left, sorry, this value isn't available. Like, what happens? What's the interpretation here? If you have anything that's left in the structure, the whole structure fails, and the first thing that is left is the error message that you get. That kind of makes sense intuitively, right? Like if we're chaining a bunch of things together, and there's some dependencies here, and one of the first one fails, we get a message about it that propagates, and we don't even bother to get the rest of it because it's meaningless, right? So that's the normal implementation of monad for either A. And we'll build on that a little bit on Thursday. And you'll find lots of other things that are monads as well. This do notation gets used in all kinds of ways. So I thought the last thing that we'll do then, after all those slightly abstract things, is go back to our live coder database and use this stuff. So I think I can leave all my tests in here because they're not going to get in the way. Let's go back up to the top here. I'll give myself a bit more working space. So we had a live coder map, mapping from locations to live coders. We have a set of live coding languages. What could we do with this? How about a function to look up? Let's do this. Let's put everything we learned today together. An I/O program that asks you what live coder you're interested in. You enter their name, and on the basis of you entering their name, it looks up in our map, our database, that live coder, and on the basis of the language that is their preferred language, tells you something about them. That's a decent task there, right? So let's write it out so that we all stay on the same page. A program to ask you for a live coder's name which it then looks up in the map database and uses to give you some kind of message in reply. So our program, we're going to follow the top level conventions for writing I/O programs you could compile and distribute as binary files if you wanted to using Haskell, which is that there's a definition called main, and it's of type I/O unit. And we can use the do notation here because we're in the I/O monad. And we can ask the user to enter the name of a live coder and then press enter. We can use getLine to get that name. So we'll get x from getLine. And then that x will be a string. And so we'll stop here and think about what we want to do here. We're going to have some function, I guess, to get a response from the string, right? So that could be maybe a pure function. We'll call it getResponse for now, and it'll be of type string to string. And the first string, the string argument will be the name of the live coder, and the string return value or result will be whatever the text is it's supposed to display. So let's not implement that yet. Let's go back to our main I/O program. We have that get response thing, so we can do put string line get response x, right? Because put string line is of type string to I/O unit. It's an I/O computation. It fits here in this monadic context. And get response x is going to be a string, right? Because x is a string, so it can be the argument to get response that gives us a string. And put string line is I/O unit, so we're done. Like that's our top level program. We're done. So now let's work on get response. How are we going to do this? Well, we have live coder map. So live coder map is a list of locations in live coders. Oh, I forgot that our map was locations. So we'll have to say, please enter the location of a live coder. So we'll do that. So we can look up in our map. Let's think a little bit outside of one of our definitions. In data.map, which I will look up here, package data.map, we have the function lookup. I'll find the. Oh, sorry, I'm in the wrong. Got to click through to data.map.lazy. Lots of things called, there we go. So lookup is our basic thing for finding something in a map. So provided our keys are members of ORD, if we have a map from K to A, we can use lookup to get a maybe value. And it makes sense that this lookup would be maybe, right? Because what if that key isn't in the map? Like it kind of has to be maybe. I mentioned just by the way that there is a lookup here. See the exclamation point? That's a lookup that just returns the value, not wrapped in a maybe. That's a very bad idea, right? Like, they're just putting that in there to tempt people, basically. You know, it's like a programming test or something like that. Because if it's not there, it's going to call error, which means it's going to throw an exception. Like, everything is just going to crash. You know, there's not really any good reason to have that in something that we develop. It's just a liability. Lookup is perfectly fine because we have some guards against the thing not being there. Okay, so lookup is going to work. Like, let me copy that type signature. Where'd it go? There's lookup. So if we do lookup and we'll say get response x. So if x is our location, and those are our keys of our map, so lookup x, like lookup location, and then we need a map from K to A, so a map from location to something else. That's live coder map, which is map location to live coder. So we can put live coder map there. That's going to give us the type of this. The result is going to be maybe live coder, right? Because our map is location to live coder. So the result of lookup with its first two arguments provided is going to be maybe live coder. And then we might want to do different things depending on whether the lookup is successful or not. So let's put up lookup x live coder map. That's going to give us a maybe live coder, but we need to get a string. So we could make a function live coder to string, and we apply the maybe live coder to that function. So now we have to write that function live coder to string, and it'll be a function from maybe live coder to string. And here we can just match the two cases of maybe, just and nothing. So live coder just x, x will be a live coder, and live coder nothing will be no live coder. So if there's no live coder, our response could be there is no live coder at that location. We'll say yet, because live coding will conquer the world before falling in on itself in a ball of fire, like all revolutions. And if there is a live coder whose value x would be of type live coder, maybe we could call show on that, right? We'll do that. We'll do this at first. This is just a first level solution. We'll come back to it and we'll make this better a couple times. But what we've done so far makes sense, and I think it's complete. I'm going to move our previous stuff away. Thanks. All right, let's check it out. I'm going to bring up the terminal. Going to reload. And our program, ambiguous occurrence lookup. Could be prelude lookup, or it could be data.map.lookup. So I'm just going to resolve that ambiguity by putting data.map in front of lookup. And then reload. We're good. Our program is called main. We can run it by evaluating main. Ask for the location of a live coder. I messed up and pushed some keys and it doesn't respond very well to my backspace key apparently on my operating system, so we'll just press enter and it says there's no live coder at that location. Let's run it again and I'll try to be more careful this time. So if I enter Dundas, and sure enough it shows me that record using the default implementation of show, the auto-derived implementation of show for live coder. Let's try it again. We'll go for Mississauga this time. And we get someone else. Let's enter something, let's enter Oakville. Not sure if there's any live coders in Oakville. There is no live coder at that location yet. So an obvious improvement we could make to this, the message we're getting back when there's no live coder seems okay, but the display of the live coder itself could be developed. Like we're just using the auto-derived show. So let's go back to our live coder here, and let's take off deriving show. This is kind of a review of yesterday. And let's provide our own instance of show for live coder instead, where show x equals. And now we've got a function that's got to go from the live coder x to a string. And we could maybe do different things depending on the live coding language too. So let's say name x, which will be the name of that live coder, will append to the string lives there. And then we'll put a space and we'll append, it could be a pithy sentence about their choice of live coding language, maybe. We'll make another function, like we'll call it describe language, and the language that we'll describe will be the maybe live coding language from language X. And now we have to provide that function, describe language, which will be from maybe live coding language to string. And here we can do like 2 layers of pattern matching. So one possibility is that they have no preferred language. And then we can give a string like, they are too cool for any one language. And then if their language is just Super Collider, see what I mean by kind of like I want to explain what I mean by this being kind of like 2 levels of pattern matching. Because we could have had our function describe language have just 2 cases, a nothing case and a just case. And in the just case, we might have used another function to like do something with all the different languages. But instead of doing that, I'm just doing one function and just matching, you know, the just and also matching what's inside the just. That's okay. You can have as many levels of pattern matching as you want. Obviously, if you're getting to the point where you're like, hey, you have 3 levels of structure that you're kind of capturing in the pattern matching, that may be a problem from a modularity standpoint. Like maybe you could refactor that to be more modular. But there are many circumstances like this where I think it makes perfect sense to sort of jump over 2 levels at once. Just Super Collider, what's the message about Super Collider? They use the venerable Super Collider language. How old school. Describe language. Just title cycles. They use title cycles and are perpetually bouncing from one algorave to the next. Describe language. Just extempore. they use extempore and are in total command of their machine. I'm making live coding jokes, subtle live coding jokes for the not yet live coders in the room. Just Hydra equals they make pretty visuals using Hydra. Describe language. Just Sonic Pi equals they are helping people learn about computers and music with Sonic Pi. Okay, I think we've covered all the cases there.
Periods outside the notation.
Thanks. And so now we can reload. Whoops. Where'd our terminal go? We can reload, run our program, enter the location of the live coder, and done this. And we get this message, my name, custom description of my language preferences. Go to Mississauga instead. Whoops. Got to run the program actually. Oh, whoops. Another attempt. There we go. And let's ask about Montreal. What's happening with live coding in Montreal? Well, Kofi's there, helping people learn about computers and music with Sonic Pi. And I think we had one more location. It was... Where did we put you, Luis?
Andy.
Oh yeah, Ainsley Wood. Yeah. Perpetually bouncing from one algorithm to the next. Ainsley Wood, algorithm hotspot. That might actually work, actually. Yeah. Yeah, exactly. Yeah. So let's do one last thing with this program and then we'll stop. So our program here has a definition in it called main that is an I/O computation, returning unit. It's an I/O program. Let's just give this the module name main, module main where, and I am going to quit GHCI, and I'm going to use GHC without the I instead on my file. And it compiles it and links it, and I should, in this folder where I am, I should have a file called day2. See the one that's lighting up in green in my terminal there? That's a compiled binary executable. So instead of using GHCI to interpret our Haskell code, we compiled it to a binary, which we can run. And sure enough, there's our program. We can distribute it to other people without the source code if we were so evil as to distribute things to people without source code. Oh, no. Yeah, and if I want to know where another live coder is, I can do this. There we go. So often when we're learning things and when we're testing little, pure, easily testable things, we might use GHCI because we can interact with those things and query them and do experiments with them right there interactively with our fingers in the terminal. But ultimately, for real systems, in many cases, we're going to build them with GHC, or we'll even see there's another compiler that we use to compile for the browser called GHC.js that compiles Haskell code down to kind of like low-level JavaScript, like JavaScript as a machine language. So we'll start to do some of that on Thursday. Yeah, so we don't meet tomorrow, but Thursday morning at 10 is the next session, and we're going to, one of the main things we're going to explore is doing this in the context of functional reactive programming in the browser. So it's a much more applied context than what we've done so far, because we've covered a lot. We've covered a lot of the Haskell basics, actually. So now we're going to move into a more applied setting. It will be useful for you to set up a build system for this browser work before we meet on Thursday. So what I suggest you do is that you look at the Estuary project, and if you can build Estuary, if you can follow the instructions for building Estuary on your system, you're ready.
How's that spelled?
Estuary. I will show you the GitHub repository. So if you go to github.com d0kt0r0 Estuary, you'll find the main repository for Estuary. And if you scroll down on there, there's a README with some instructions about building it and trying it and stuff like that. The instructions are mostly about Debian Linux. If you're on Windows, it can be done, but it's awkward as hell. I can ask Spencer, who works on the project and who often is working on Windows, if he has some instructions about how to get that working. If you're on Mac, it's usually more straightforward. Anyway, maybe we can do some of that during the session too. I don't think I have a fully prepared recommendation here. Just to say that if people are able to build Estuary, that means they have a valid build system for GHCJS, this alternate compiler that we use. And so you'll be really ready to try things in the browser that we do on Thursday. Any questions or comments? Yeah.
People on Windows 10 could try the Linux subsystem for Windows 11.
I think that's how Spencer has got it working.
Mm-hmm.
I think it's still a little bit fragile. With the question is that probably people could use the new Linux subsystem on Windows 10 to get this to work, and it seems like there has been some success there, but it's fragile, like any of these things. So I will ask Spencer, because he might having done it many times, he might have some specific things to watch out for, and we should really add it to the instructions too here, because it's such a common case. Of course, if anyone who's running Windows and is going to do this work this year wants to dual boot their machine with Linux, that's not a bad idea, frankly, too. Like, I have always found that useful for these kinds of things. All right. Thank you, everyone. See you on Thursday.